Okay, we are going to see the presentation from Zarketa-Astigarraga from the Universidad de Mondragon, Optimization of Wells type air turbine for OWC wave energy converters under realistic wave climates.
Thank you for the presentation. I'm sorry for the tricky surname. First of all, I have to say, well, I must say that this is a collaboration with our university, with our industrial partner, ENAEM, I must say that, and that it constitutes one of our first attempts to develop a semi-empirical approach to optimize Wells turbines, okay, with an analytical tool. And the second point I want to stress out is the part of the realistic wave climates that it's on the title, okay, you will see why. Now, I will try to go as illustrative as possible and not to bother you with unnecessary details. I guess that we are all minimally familiar with the OWC plant that I'm showing at the left-hand side of the figure. So the wave comes, we have designed the chamber so that the wavefront enters in resonance when it comes. And when the wavefront goes up, it acts like a piston. It takes the air away from the chamber, and such an air front activates the turbine that is here, okay? And likewise, when the wave goes down, it swallows the air coming from the atmosphere, and due to the self-rectifying nature of the turbine, which is a Wells-type turbine, well, it acts equally well, okay? So that will be the framework, and precisely we'll be dealing with a Wells-type monoplane turbine, like the one shown at the bottom left-hand side figure. And we will be optimizing the geometrical parameters of such a turbine that are shown at the rotor plane, which I'm showing at the right-hand side here, okay? So there are plenty of geometrical parameters that enter the design, the number of plates, the solidities, the up-to-tip ratio, the omega, okay? And all that will be introduced somehow in this semi-analytical code that we are developing, okay? That's for one part. For the other part, this figure serves as well the purpose of showing which is the fundament of the blame element method that we are adopting as a solving strategy via this radially split blade, okay? Now we are splitting the blade radially for discretizing the blade as in a simulation, and we are considering that each blade element constitutes a two-dimensional linear cascade as the one shown upside, okay? So we introduce some inflow parameters, we solve for the inlet velocity triangle, we go through the aerodynamics of the airfoils here, which are considered as NACA standard profiles, and then we solve the outlet velocity triangle. With that, we compute the differential power and torque coefficients, and we integrate that radially for getting the power and the efficiency of the turbine, which at the end of the day, what the semi-analytical code is yielding us is a number of dimensionless parameters: the flow, the power, the pressure drop, and the efficiency. Now, the problem with those parameters is that they are steady. They do not have the information about the variability of the sea state. Now, in order to account for such a variability, we follow the approach adopted by Falcao et al., who say that you can somehow calculate a sort of averaged dimensionless parameters whenever the sea state is liable to be described statistically. Now, we will assume that such is the case, and that we have a Gaussian PDF for the dimensionless pressure variations that we have on the chamber, and with the convolution-like operation that we are taking here, we'll be introducing just the average parameters or the average counterparts of these parameters here, okay? Now, for reasons that I will explain shortly after, we will be mainly interested in the evolution of the efficiency curve, okay? So at the bottom side of the slide, you have both the static and the stochastic efficiency curves. Now, the differences I want to point out on these two graphs is that, first of all, we are not plotting the same thing on the x-axis. We have the dimensionless flow coefficient here, whereas we have the dimensionless standard deviation of the pressure coefficient here, okay? That's for the one hand. For the other hand, we see that the peak of the static efficiency is relatively higher than the peak of the stochastic one. And that's because of the convolution-like operation with a Gaussian PDF. Okay? And the third one, which goes for the same reason, is that we do not see such an abrupt drop, which is really characteristic of the Wells turbines, in the stochastic counterpart. This as well is smoothed out because of this operation here. Okay? So with all that information, we can describe the optimization strategy we are carrying out. We start by introducing some turbine configuration, and we compute the steady state curves for a given C state. Now we focus our attention on the 5-psi curve, as shown here, that we know that it is a linear relationship between phi and psi for pure Stalin conditions. Okay? So this is linear, we calculate the slope k, and we know that such a k can be related to an input parameter that it is a C state related parameter, the damper coefficient, and the omega, or the rotational speed of the turbine. Okay? Now, if this is given and k is given, we can calculate the omega, or the rotational speed at which the turbine will be operating. And we have, as well, a pre-established interval of accepted rotational speeds. Now, that's not just for safety issues, it's also for avoiding compressibility effects on the semi-analytical code, okay? Now, if it happens that the rotational speed we are calculating falls outside the pre-established interval, we set the efficiency for such a C state to 0. If it doesn't, and if it falls within the pre-established interval of accepted rotational speeds, we proceed by calculating the stochastic curves, and we enter into the efficiency curve with the dimensionless standard deviation on pressure. We read the corresponding stochastic efficiency, and we repeat that iteratively for each C state. At the end of the day, the score or the fitness we have is a kind of a weighted sum of such stochastic efficiencies with some weights, and those weights are represented by the probabilities of the C states. Okay? So this will be the optimization strategy. What do we do with all of that? We go to a specific case study with the Marmok A5 device, which is developed by IDOM and has been deployed at the BMEP site in the Basque country. And the point with this particular device is that it already constrains some of the geometrical parameters, namely the number of blades, the gap between the blade and the casing casing radius, but we still have plenty of room via the height-to-tip ratio and the linear variations of both the NACA profiles and the solidities for optimization. As the point is to see how the optimization works in different sites, we will be launching our campaign at BMEP in the Basque country and at IMEC in Scotland, because they have really different or relatively different C state conditions. We take the 30 most energetic C state conditions and we compute the normalized available power, the damping coefficient, and the dimensionless standard deviation of the pressure, and we let all the loose geometrical parameters vary within these ranges here. We enter with that to the optimization strategy I have described to you just 2 slides before. And what we do is that we wrap all that in a genetic algorithm framework with 200 individuals as a population, and we let it run for 200 generations. Sorry. What do we obtain? Well, here are the preliminary results. If we go to the left-hand side of the slide, we can see the table that summarizes both the BMEP optimal and the IMEC optimal configurations. And at the bottom, we can see an illustrative example of how the geometry of the turbine varies when changing from BMEP to IMEC. Now, what it seems is that the IMEC optimal configuration is asking for a lower height-to-tip ratio and lower variations of the chordal distribution along the radial direction, which means that the IMEC optimal turbine is somehow asking for lower blockages of the pipe. Okay? Besides, it seems that the NACA distributions are not playing as relevant a role as the height-to-tip ratio and the solidities. Now, how does all this translate into the behavior of the turbine, into the stochastic behavior of the turbine? If we go to the right-hand side, we can see the two stochastic conditions on the top of the figure, and this is run at BMEP with the two optimal turbines, whereas this here is run at IMEC, but for the two optimal turbines. Okay. Now, what we can see, these points here are indicating the operational points. What we can see is that the BMEP optimal turbine seems to prefer to operate near the peak of the stochastic efficiency, whereas the IMEC optimal turbine seems to distribute its operating points along the far post-start region. Okay? How is that translated into the C state or specific C state condition? We can see that in the cumulative plots that are at the bottom of the figure. What we can see, there are two main takeaways that we can draw from here. The first one is that the BMEP optimal turbine seems to be much more robust than the IMEC optimal one, because it obviously outperforms the IMEC optimal turbine when run it at BMEP, but it just has a drop of 15% in the overall efficiency when run it at IMEC, whereas when we run the IMEC optimal turbine at BMEP, we show a 38% drop of efficiency. Okay? That's the robustness shown by the BMEP optimal turbine. And the second takeaway, and for me is the most relevant one, is that it seems that the two turbines follow a different optimization strategy. The BMEP optimal one seems to prefer to shoot the specific C states where it can, so to say, obtain a given stochastic efficiency, whereas the IMEC optimal one shows a much more distributed and gradual cumulative plot. Okay? And that is showing that the approach adopted by one and the approach adopted by the other, of course, the geometrical parameters are different, but it is not so obvious that the optimization strategy followed by one and by the other are so different. Okay? So conclusions, the first is that the hat-to-tip ratio and chordal distributions are relevant design parameters, not so much the NACA distributions. The robustness of the BMEP optimal turbine configuration, as I have just said, and the different optimization strategies followed by the optimal turbine configurations. That was all from my part. Here you have a little list of the references I have been addressing throughout the presentation, and please, if you have any questions, feel free to ask. I will do my best to answer them as good as possible. Thank you.
Okay, we have enough time for questions.
Thanks, Markel. That's a very interesting presentation. I'm just wondering what assumptions you might have made about how the OWC turbine is controlled. Do you assume, for example, that the control system maintains the optimal velocity at the peak efficiency?
Yep, the assumptions here are, first of all, that the rotational speed is kept constant. Okay. That's the main assumption we are doing. We are not entering so much into the control system. That's the second part of the work we are developing currently. But so far, we have just dealt with the aerodynamics part, not with the control part. But yeah, we are assuming implicitly, I have not said that the rotational velocity is constant.
It'd be interesting to see if it changes your design very much, and it goes back to Damien's presentation of, control co-design, and to see what sensitivity there is. Maybe there isn't a whole lot.
It's just a spoiler alert. It does.
All right.
It does change.
Thanks.
Any other question? We have time for another question.
There's no problem if there are no more questions.
We need curiosity.
Excellent. Thank you very much. It was a nice presentation. I was wondering, I was taking a look at that. I'm not really sure, because I have never worked with OWC. So why are you assuming actually that, why do you want omega between that interval to consider zero, different from zero efficiency there, because you...
You mean this one here?
Yeah.
This condition, the conditional?
Yeah.
Well, That constraint comes from the client side. That's because if you are running at a really high rotational speed, first you have structural issues, vibrations and so on. And second, you can, and that's from the fluidic part, you can have compressibility effects. And if you have compressibility effects and shock waves, that means that the equations are not elliptical anymore, they are parabolic, and you can transmit information not just downwards, but upwards, and you can affect your chamber. And that invalidates all the analysis we are doing here. That's why.
Which kind of algorithm for optimization do you use there in the loop?
I didn't really catch that. Can you repeat that,
Yes.
please?
Which kind of optimization algorithm do you use in the loop of
This is a genetic algorithm.
Okay.
Yep.
Okay.
Well, very good presentation. I'm really interested in this topic. You mentioned in one result that one turbine is more robust than the other regarding the results. You consider that the robustness here in this case is an advantage, or you prefer that each turbine fits better each sea state or climate?
It really depends on what you are looking for. I mean, I think that the most relevant conclusion from here is that we are going with a weighted sum as a fitness function. But this is telling us that you can have different fitness functions for different purposes. And that's what you have to decide as a designer.
Okay, thank you very much.
Okay. Thank you, Ander. And we will have our last